In this session, I will introduce the secure key management system developed by Line blockchain and its underlying Intel SGX. Line is developing a blockchain platform trading NFTs and user tokens, including the cryptocurrency Link. Currently, Line blockchain is a private network. And to make an open network or to connect with nodes outside the data center, we are redesigning it on a daily basis with ongoing validation. Now, some of our system's challenges have been solved by the properties of the blockchains, but others have not. For example, when connecting to an external node, it cannot be safe because it is behind a file, as has been the case up to now. And in an environment such as the cloud or outsourcing, you will face challenges such as whether the confidential data is being handled properly and whether someone is physically trying to steal it. When it comes to the consensus part of the blockchain, the equivalent of confidential data is the secret key for corresponding the block. If this is abused, it can result in fraudulent transactions being signed with an approval signature, affecting the reliability of all services provided by the system. And if we protect confidential data through encryption, any system will eventually come down to the same problem we have: how to correct or protect the key for that encryption. To address the issue of how to securely manage this data, which is generally a few dozens to several hundred bytes in size, we will introduce a Line blockchain's KMS, key management system, which we developed using Intel SGX technology. Although this KMS is very small and simple in configuration, the mere fact that this is very small system can handle keys securely can have a huge ripple effect on the security of the entire system. The amount of damage caused by the outflow of crypto asset on the blockchain is getting bigger every year. A quick search of the news reveals that this year it is equivalent to $2 billion, or about $3 billion, or 440 billion yen, according to blockchain analysis company just this year. So 440 billion yen is stolen. And at the presentation, we do not have fixed information, and last week there was a case as well as fraud last week as well. So this would not only about blockchain, but also the new one recently is ransomware. So you might remember about the cases in Osaka, hospitals in Osaka. So this is a type of attack that encrypts the system's critical data and holds it for ransom. Ransomware is impressive in that it demands a huge ransom, but if it is that intrusive, it means that there is a good chance that your confidential data has been quietly stolen and is being used for the next crime. So, keys. How should we handle keys? If no special measures are taken, keys will be stored in local storage. Even if you encrypt, then enter the passphrase at some point or decrypt it, and place it in memory in plain text. So we need to consider cases where input or memory is read during execution or can be output when a memory is paged out, or when a process terminates abnormally and score. Thus, there is only so much an application can do against attacks that target hardware or OS behavior. So a method that is currently considered relatively safe is to use keys that are sealed in hardware that is called HSM, a hardware security module, a dedicated device. The price varies from inexpensive USB types priced at around several tens of thousands of yen to expensive ones for enterprise system. By the way, I brought this USB type one. So this key, can you see it? Thank you. So it's so small. So within this USB circuit, the key is sealed. And if you try to destroy it, the entire circuit is forcibly opened. It's called tamper resistant. And since the encryption process is performed in the circuit, there is no fear of the key being read. However, it's very small, so the cryptographic processing inside is very small, and so the speed is very slow. So I will put this away. Non-USB HSMS includes PCI devices and servers that use them, as well as box-shaped set-top boxes. They have better performance than USB because of their more power and area advantageous construction. The cost is a little higher, but vendor support is also available, which may be good for enterprise systems.
The final consideration is TEE, Trusted Execution Environment, so using this technology. TEE is supported by hardware and uses a secure process execution space created on the computer. The most significant difference is that HSMs can only use fixed circuitry-based functions. TEs can perform their own cryptographic algorithms and cryptographic operations. The key is sealed in the hardware, that is in the CPU circuitry, so cannot be extracted, and the encryption process uses the CPU performance of the machine, making it very fast. So which method is the best? Let's look back at our requirements. Cryptographic techniques used in current blockchains often utilize algorithms that are not internationally standardized or implementations that are not yet common. For example, quasi-isomorphic cryptography, secret sharing, zero-knowledge proofs, and quantum computation-resistant cryptography. Indeed, our Line blockchain also makes use of VRF proofs and the ability to use BLF signatures with pairings. So I will omit the details because if I start explaining, it will take too long. And we need to really move on to faster algorithms. Programmable is the most difficult or the tricky part of the requirements. Commercial HSMs only implement commonly used cryptographic algorithms. Therefore, our choice is to use TEE. From Intel SGX was our choice due to the scale. And there was a team who has been developing this before ahead of others. So we had them share the information, and we started prototype development. In the next session, from 5 p.m., there will be a talk on SGX in the Security Center's solution presentation. So if you're interested, please listen in. Now, I will explain the overview of Intel SGX. Intel SGX is a technology that encrypts a portion of the memory space with the assistance of hardware. And programs and data loaded into this encrypted, trusted memory area cannot be read. So even if it's read, it cannot be decrypted. And because it is encrypted, the executable instructions in memory cannot be rewritten to add steps or tamper with jump destination. And this encrypted memory space is called enclave. The processing in enclave is not carried out in a completely encrypted state, as in quasi-isomorphic encryption, but instructions and data are decrypted by hardware and processed when they are placed in the CPU cache. So this means that even though it is encrypted, it is not significantly slowed down, but instead leaves open the possibility of side channel attacks targeting CPU, such as SGX Spectre. So whether that is possible is a different story, but theoretically, HSMs are still said to have an advantage in this regard. And Enclave offers about 94 megabyte. In the slide, it says 92 megabyte, but it should be 94 megabytes, 94 megabytes instead. How SGX applications work, it can be broadly divided into two parts. First, the process that run on Enclave. So these are in fact ordinary functions implemented with C. These functions are built as shared libraries. So these are linux.so files. The application simply loads that library and calls these functions. So in reality, you have SGX in between, but it's transparent, so it does not do anything special. And the developer develops a library that works with Enclave and an executable file that has a main function, respectively. The process that runs on Enclave, the limitation is that CPU operation and SGX functions can only used. So overall, OS system call cannot be used. So file I/O, file storage, and outputting debug information, how can we do that? So you have to go back to revert to the untrusted process. So it's returning the function invocation, or by calling the application function backwards from Enclave. Of course, the data passed to the application is exposed to the untrusted space. So if it's confidential data, it must be encrypted in the Enclave. Next, let's take an in-depth look at the development flow. This page shows you what you need to prepare to develop an SGX application. And it shows what you can do when you build them and where they will run at runtime. So this is perhaps the most minimum route possible. And although it may seem a little complicated, it is easier to read and understand the makefile if you have seen this flow first. The goal of the development is to create two files, a shared library that works with Enclave and an executable that uses it. These two files at the end of the build phase are the goal. To do this, you need to first create source files for the application and for the shared library respectively.
Then a file called EDL is created for Enclave and application to call functions from each other. This is a field that serves as ideal interface definition language. EDL files are converted into source for applications and source for shared libraries using the command edge-rater. And file, just for information, the T in the file name stands for trusted and the U for untrusted, and these two symbols often appear in SGX naming. Finally, sign the library so that the shared library can work with Enclave. This signature has several important security purposes: to detect program tampering and deny loading into Enclave, or to prevent data encrypted with one library from being decrypted by another library, and to use attestation described below. Therefore, Since the private key used for this signature must be treated the same as the confidential data, it is recommended that HSMB should be used here. Now, an SGX application created in this way can be run just like a normal application with only a slightly special build procedure. SGX application can also be built in simulation node, so they can be built and run on machines that do not support SGX. Now, assuming that a trusted memory space is available from the applications, let's actually consider the design of how to handle the key, a confidential data, and how to implement our signature function using it. The first step is the setup phase to make the machine ready for services. And this is the place the key for signing is created. You would generate a key pair for signing with an enclave and then encrypt the private key using the SGX's encryption function. Then the private key can now only be decrypted within this enclave. That is, it can be used within the enclave. This encryption by SGX function is called sealing. This sealed private key is passed to the application and stored in the local storage of the KMS. So the public key corresponding to the private key is not the data that should be kept secret. So it is stored as it is. So even if this is stolen, this would not be a beneficial information to attackers. Then the service is launched by initiating KMS. The KMS and blockchain mode is separated by firewalls. So there should be a hole generated from outside. So from KMS side, the blockchain needs to be connected. This is a special function. So they are trying to connect from servers to clients. So it's not an RPC framework. However, they would start connection by themselves. So when the connection is established, are they really the appropriate opponent? So that requires a handshake procedures. And here, they communicate using station-to-station protocol, a TLS-like method in which connections are authenticated to each other, encrypted, and impossible to conduct man-in-the-middle attacks. The intended signature function of the KMS is performed as a simple request response using an already connected TCP connection. Upon the receipt of the signature request, KMS passes the sealed secret key with the message to a function on the enclave side. The function on the enclave side unseals the private key with SGX functionality, generates a signature for the message, and returns it. Finally, the generated signature is returned as a response from the KMS to the blockchain node.
If the sealed data can only be decrypted on that specific machine, how can it be backed up in case of hardware failure? As a matter of fact, key backup is not a requirement in our case. This is because the keys for the blockchain consensus are used for signing, so the loss of the key can be dealt with simply replacing the node. So it is only necessary to prevent the private key from being misused. Having said that, but if you have encrypted data, you will need to back up your keys in case of decryption. So we would like to introduce you one design we thought of in the beginning. However, this has not been validated yet. So SGX could use a mechanism called remote attestation, which used a trusted third party. With remote attestation, an authenticated and secure channel can be established between two SGX nodes. And using this, sensitive data can be copied to another SGX machine without exposing it to the outside world in plain text. This mechanism is similar to TLS client-server authentication, which uses a certificate authority, CA, to authenticate each other. Apart from using remote attestation, the most easiest method is to relax the security a little. The setups and make the setup take place in an isolated, trusted environment. If that is possible, you can use the same key in multiple nodes. But that key must be stored in a safe place isolated from the network. Now, I will share one more design related to the extensibility of KMS. The structure of KMS application is divided into remote procedure call part and backend part, and the backend is modular and replaceable. The backend for this SGX implemented, as described so far, we have another testing backend. That is not safe, of course. But for testing, for CI, well, this testing environment has KMS full functionality. And other back-end implementation is HSM. So that is another possible back-end implementation. In the future, if an ACM that implements all the functionality we need were to be commercialized, the current design could be used by simply implementing and replacing the back-end part. Alternatively, when we support other TE technologies other than Intel, or in the future, when a new incompatible successor version of SGX appears, we can change the functionality without significantly changing the basic structure. Now, if we compare the current SGX backend with the mock backend, we will be able to measure the enclave overhead. Now let's look at the performance. So we would like to go over our requirement. Firstly, the functional requirement to be programmable is achieved by implementing our signature function on top of enclave. Security is also achieved by the fact that keys are not exposed in plain text and are handled in an encrypted memory space. As far as throughput is concerned, that is not really important in our requirements. So, acceptable throughput is about 5 milliseconds. And as a result of the benchmark performed after KMS, the latency of 0.62 milliseconds and throughput of 1600 TPS for ED25519 signature. And VRF proofing, which is not so fast because the algorithm itself is heavy to begin with, also showed a performance of 1.8 millisecond, 555 TPS in throughput. Thus, the performance requirements of KMS implementation have also been met. So if we are getting more than 1000 TPS in normal signature, we can consider it on par with an enterprise HMS solution. Finally, let's look at the costs. The machine used for development and testing was Dell Optiplex 7070SFF. This is a small desktop PCs that normally cost less than 100,000 yen second-hand. So there were no special costs for SGX here because the specs were very general. So the cost requirements were met. So we did it very well. As a result, we have a programmable and secure key management system with performance comparable to commercial HSM solutions at typical development and server operational costs. However, it is not all good. So I will give some few observations. The degree of freedom is a little low because you need to select and procure an actual device that supports SGX, especially development models. The Intel core processor no longer supports consumer, and this will be less available in the future. And also, BIOS settings, OS kernel, and SGX driver, the combination, maybe you will have to go through some trial and error. In terms of development, we had to rewrite some open source libraries because random numbers was obtained from system entropy, and signals were partially used. And this needs system calls, but enclave cannot use system calls. And in the SGX build, we'll then have their linking C standard libraries like libstandard-D was replaced by the SGX versions. This means that implementations of memory manipulations functions such as mem-CPI are rewritten to work safely. So we recommend you to test. And this time, KMS was developed in Rust, and only enclave and its calling parts were implemented with C. So that is working as expected with no particular problems. If we had more time, the enclave implementation itself could have been done in Rust. About the build. There are many options, such as specifying EDLs and signing keys, whether to simulate or release, and whether it's a release build or a debug build. So there were many options. And the make files tend to become complex as a result. So overall, there were some findings, but the execution and operation did not see any problems. And compared to C or C++, we didn't see much confusions. Looking back on why we built this key management system in the first place, it was to build the next blockchain networks, Ebony and Finshare, and to give a higher and more advanced security architecture. And this key management system has no plans to be open source, but the KMS is currently ready for closed beta testing for Ebony network. This session introduced the development of a key management system using Intel SGX technology. So in our case, the target was blockchain. So we hope that it gave system designers and product planners a hint to imagine how they can apply it to their own system functions, such as sensitive personal, financial, medical, biometric, and software license management. Software development tends to favor being independent of specific hardware. This barrier of resistance can be a differentiator, a barrier to entry, a product strength, or in case of individuals, a special skill. So I will recommend using TE technology to plan and develop more secure products such as the new Lime blockchain. So that was Takami from Blockchain Lab. Thank you for listening.
Thank you very much, Mr. Takami. So from now on, as last hope, we would like to go into the in-depth session Q&A by the questioner. So we would like to incorporate your questions as well. So if you have a question, on the right bottom of the screen, there is a question mark, and you can use this button to post your questions. I welcome your questions. And the question is asked by Mr. Shogo Hyodo. Would you please introduce yourself? I am Hyodo from Blockchain Engineering team from Line Corporation. It was a nice session. Thank you very much. Personally, so Intel SGX, that's my interest as well. So I was watching with interest, and it was a very beneficial session. So let me ask you a question, may I? Yes, please. So one of the things that I was thinking about is this key management system. There are many key management systems developed. So is this true? So you talked about KMS. So based on the existing system, I think you modified and improved the system. Is that what you mean by that? When it comes to KMS, you talked about this KMS, key management system that I covered here. We did some research before we start this. So Tendermint KMS, that's one thing. So it's more like that type of position. So that was the purpose of our development. But TMKMS, it's not SGX, but it's HSM. So we showed you mini HSM, this device here. This HSM specific KMS. It was this HSM specific KMS. So it does not require our requirements. Therefore, we try to implement something new. Originally, so in Java, so Java standard toolchain include some kin tool as well as key store. So those are, it's a key management system utilizing local management store. So and I have no knowledge about that, so I refer to that knowledge as well. Oh, I see. Thank you very much. So Tendermint, I think it's close to Tendermint in my impression. So you refer to Tendermint. Yes, that's right.
So you talked about Tendermint, so I have a related question. Other than blockchain using Tendermint, for example, Bitcoin or Ethereum and Polkadot, so that type of blockchains, the philosophy of key management and a development of a key management system for those type of blockchains. Okay, in other blockchains, the implementations are varied, so I'm not sure about the most detailed branches, but that is an area which is not really discussed very deeply because using VRF attestation like us or VS, so they don't do anything tricky like that. So most prominent blockchains, key management systems can be handled by using HSM. That is my impression. I see. So personally, when I look into Ethereum, recently in the Ethereum switched to POS, but they don't really, I haven't seen any discussions on key management happening. And the KMS that you introduced in this presentation, does it support Ethereum or other blockchain? If that is possible, this will be a more generic KMS, and that will be very interested. Is that possible?
Yeah. So this is SGX. So basically, as I mentioned earlier, so CPU processing, if we can use CPU processing and it makes it, then well, basically, I don't say everything, but those that are used in major blockchains, the encryption processing in those and bringing those encryptions to KMS would be possible, I think. So do you have any specific common protocols in plan right now to generate? So standard-based KMS interface, if we can standardize in this way, that would be usable for generic purpose. It's up to the capability whether we can make up that type of organization or not. Yeah, I'm expecting that. Thank you very much.
And I belong to the same team as Takami-san, so I'm familiar with the situation. KMS you are building it by yourself, more or less. So maybe you could really reflect your own preferences. So what kind of preferences did you reflect into this KMS that you developed by yourself? Well, I just developed it. That is my simple answer. The KMS is for special purpose. And I like building minimal servers, which is for certain use. So these type of mini server that I build on a daily basis, and I was able to implement that and develop that. That is the KMS. By the way, I have a web page. My web page is powered by a server that was developed by myself. That's what I do. So like everything else, I did it. So you're very good at it, and you used your strengths. And there are questions from the audience.
So I have some questions from the audience. So let me pick up some. So the first question: SGX vulnerability is sometimes reported. So what type of actions are you taking right now to those vulnerabilities? So how do you feel about that? Well, fundamentally, so SGX Spectre, just that I mentioned earlier. So there are some comments about that type of thing. So rather than taking actions, we accept them as risks. That will be the answer. So accept them as risks. That means you should be patient about that, or you should take it as it is. Well, that's one thing. But also from the point of operation, so this SGX Spectre type of attacks, that level of attacks should, the attacks should not reach that type of level from the point of the operation. That is the intention of that. Okay, thank you.
The second question. On the security side, FYTS 1402, we think about these type of approval system, and authentication, you can get the challenge. And the system which was developed, I want to know whether they have received the authentication. So we did not. So it's not yet open source. So there's no certification. So we are not really ready to offer this to be used externally. So this needs to be used in a safe environment, which is separated by the firewall. That is the situation. So whether you will make it public is something that you will think about going forward. Right. So separating out the key management to make it in a safe place. So that is the first step.
Thank you very much. So let me move on to the last question. So we just covered to some extent. So what are the things that you would like to try in the future? Well, as for the future deployment, so in the case of blockchain, so secret distribution and zero knowledge proof. So there are some blockchains that include such kind of features. So utilizing Intel SGX this time, so signing as well as verify proof was done. So in the next stage, so we'd like to make up some security functions based on these. And also, it's not only about blockchain, but in this case, so machine learning is also a hot topic. So after you gain privacy, so there should be some cross aggregation. So that type of purpose can be utilized, achieved. So based on that, if you, I was wondering whether I can come up with nice ideas. So security, privacy. So in those areas, I think Intel SGX will be very beneficial because of the level of freedom. Yeah, the new theory is easy to bring in as well as easy to implement. So in that sense, I think it's an advantage for that.
Okay, thank you for the session.